Hello, everybody. This is going to be our video lecture on SCAN. It's definitely a fundamental tool in your parallel toolbox. Um, and so let's get into it. So first of all, I have today's quiz. It's everyone to pause the video and check it out. Just try to complete this whole thing. If you have trouble like filling this part out, at least, I can understand maybe this. I should be able to hopefully figure this out too, but if you have trouble figuring out what SCAN is and figuring out like how to do the prefix sum, I would suggest going back and just watching this video. It's only a couple of minutes. And with that, I'll allow you to pause the video and then we'll kick back in. All right, so we're back. So let's talk about this real quick. So hopefully everyone was able to sum this up. The sum scan or prefix sum of any set of numbers is just the sum of all the numbers that come before it. So like this one is 1 and this one is 3, and let me center this so it doesn't drive me crazy. Okay, so that's 3, and this one is, well, you can either add up 1 and 3 and 3, or excuse me, 1, 2, and 3 and get 6, or you can just add 3, the previous one, and this number. So this is how I end up doing it is, 10, 15, 21, 28, and 36. Okay, and so just to go back to presenting here, you sort of have this end up with this dependency where when you're adding it, you can either add them all up every time and make this n squared algorithm. But just really easily, you can just sort of look at the previous value and add it up. So when I go here to, when I'm done computing this one in my sequential version, right, I just add the new number to that number and I get 15, and I add this number to that number and I get 15. What you end up with is sort of this dependency situation here, which if everyone wants to pause the video and just come up with what they believe the work and critical path length of this algorithm are. Okay, so hopefully all of you guys got both of them to be essentially n. That there's about n amount of work here, and the critical path length is n, because I have this set of dependencies where each one has to wait for the computation of the previous one, and so it's rather difficult to parallelize. One of the things I really like about SCAN is it has a perfectly fine sequential algorithm that then you have to just think about it a little bit differently to get a better parallel algorithm, or one that has a better SCAN. Okay, so I could go through and re-explain this algorithm. I feel like that'd be just a waste of time when there's already this video that exists that you can just go ahead and watch. So if you don't understand, or if you get confused by Hillis and SteelScan, just go back and watch this video. It's only a couple of minutes, and definitely hop on to office hours for help if you're confused. If you do that, like, be prepared to see this wonderful circuit diagram. I love talking about this. And this is hopefully will help a little bit. I like to think of it as like, if you imagine trying to sum up this value, right? You can see this sort of thing where it sort of gets this value from there and that value from there, right? And this one pulls those two, and this one pulls those two, right? And you can sort of go back and sort of find that, oh, in fact, it's grabbing all these values to sum them up. It's just doing it in this kind of log phase way, like log number of the number of things you need to add up. By doing this sort of like doubling every time the offset that you're pulling it from, you end up, the sum of this guy ends up pulling it from this kind of tree-like structure where you grab all the values in this sort of not just a very clever way. Okay. Some of the code to use to get this studio to work, the powers of 2 iterable studio and phasable int arrays, which we're going to introduce now. When I had the power of 2 iterable studio, I wanted everyone to have experience with iterables. It's not a very parallel construct, but it felt like people were struggling enough with fields and stuff like that, and just interfaces, that we needed to have an iterable. I might as well make it the powers of 2 iterable, because it'll come in handy right now. Because as you notice, the offsets that I'm grabbing every single time, the offsets between what I'm adding is 1 here, and it's 2 at this, excuse me, it's 1 in this phase, and 2 in this phase, and 4 in this phase, and 8 in this phase, and it just grows that way. You can do this with just multiplying by 2 live. What tons of students do is they call the POW function and convert it to an int. which drives me crazy. So don't do that. But if you make a powers of 2 iterable class, then you don't have to worry about the _I final situation. So hopefully that'll all pay off for you guys. The other thing I want to introduce is this phasable interarrays. One of the aspects of SCAN is that it has this wonderful log n span associated with it, or a critical path length, but you end up having to use a bunch of memory. And we could allocate a new array of memory at each phase, but that would be a little bit too wasteful. So let's just have it so it swaps back and forth between things. And so there's a bunch of different phasable objects. You can look into them. The one we're going to use is phasable interarrays, where you pass in some original data. It will not mutate this. And it creates 2 buffers, if you will. And so when you call get source for phase, it'll return back the right one for whichever phase that is. So source is where we're going to read from here for a particular phase that we're on, and we're going to write it out here. One of the questions you're going to have to face is which one should your function return when you're doing scan? And so I'll leave that as an exercise for you. But you're going to leverage this as you're going through by phase by phase. So this is phase 0. You're going to want to read from this array and write out to that one, right? And when you're in phase 1, you can say, well, just give me the source. Well, that will read out the previous guy, what you wrote out, kind of thing. So hopefully that will help you to build this studio. Like I said, it's a useful tool in the parallel toolbox. A lot of times I feel like we don't have enough parallel in 231. This is not one of those moments. Scan is definitely a primitive that is available and is a very useful tool. What I also like about it, like I was mentioning, is it's this perfectly fine sequential algorithm. There's nothing wrong with how I described that set of dependencies. And if you were building a sequential algorithm, that's how you should do it. But it also requires, like, it feels like something that has this, you know, just has this inescapable set of dependencies, right? Where it's this, my work is n and my critical path length is also n. But if you think about it in a little bit different way, you can get that span down to log n, which I really like. Let's talk about the next one. So for those of you who get through that and want a little extra challenge, you can build Blaylock scan. And so this is has more steps or more phases, if you will, but much less work. And so this is an alternate version of it, a different way to approach it, and a little bit more challenging, I think, but definitely an important tool. And I've scaled this down a little bit just to get a sense of like the number of phases, right? So this one has less work, and this one has like sort of a shorter critical path length, if you will. And I just want to note they're not asymptotically different. So this one has sort of like twice as much work, but not like you know, like it's not n work versus, excuse me, it's not like n squared work or n log n work or anything. Just sort of twice as much work. And this are sort of a constant factor more work. And this one is a constant factor of more steps, sort of like 2 log ni. And so they're both useful, and just thought I'd expose you to both of them. Okay, so a bonus one is for your life after the studio. There's something called, in Java, there's parallel prefix. Sometimes scan is called prefix sum, and you can do it this way. Obviously, do not use this. This would be considered shenanigans if you were to call this and then just do some for all loop to pass all the tests or something, or a certain number of for all loops. But just wanted to alert you to this is a tool that should be available to you when you move on in sort of different languages and different contexts. So the second part of this quiz asks, all right, so given this array and a predicate that says, all right, if the continent name contains C, then that returns true, right? Then I want you to produce this array, which has just the continents in this case that have C, so Africa, South America, North America, and Africa. So my first question to everyone is, what would you call this process? And so if you haven't thought that out, pause it now and come up with what your answer is. And we'll talk about it. All right, we're back. So I'm just going to tell you what this is typically called, or what I've called it. This is called PAC. There's nothing wrong if your name was different. I just wanted everyone to think about what they would call this. Um, the act of taking some array and some predicate, and then everyone who passes that predicate gets packed in, that's just called packing. So that's what we're going to call it. And the next question is, what would be difficult to parallelize in this? I'll pause for a second. All right, so hopefully you thought about it a little bit. This is a very typical problem that happens, is that it's really easy to parallelize and have everyone figure out which side, whether or not they're in or not. Okay, so I can make a parallel for loop and say, do you have a C in perfect parallel, right? And everyone can know whether or not they're in this array completely independently of everyone else. The problem is that nobody knows where to write themselves, right? So like Antarctica can't, without talking to its friends, figure out where it's supposed to go. Like, how big is this array in the end? Like, I know I'm in, but I don't know that I should go in slot 3. And North America doesn't know it should go in slot 2 without some information from its neighbors. So that's the difficult part to parallelize. That is a very typical problem. Like, it's really easy to operate on every element in an array, for example, but it's really hard to tell where it goes, right? And so we're going to build the PAC Studio. Guo Zhao helped out greatly with this. Let me take this due date out. And so let's talk about just sort of the first step. I'll give everyone the first step, and you can look into this further on the wiki. But the first step for this is, if everyone can immediately tell whether they're in or out, right, it would be really easy for everyone to write out into an array 1 or 0 based on whether or not they're in the final array. Okay, and I'll leave it to you to figure out how to make it so PAC can work. I'll give one last sort of thing to comment on this arena, is that I've alluded throughout the class that you can do parallel merge sort. You can do the combined step in parallel. You can also do the partition in parallel. And to give you a little bit of hint on this, like, it involves scan and the same sort of approach that we're building with PAC. PAC is just I feel like gets you to the core problem in an easier setting than Quicksort. Quicksort just has a little more complexity to getting it to actually work, whereas PAC has the same fundamental problem, but a little bit easier to get to actually work. Okay, and with that, I'll say good luck, have fun, and point everyone to the office hours if you need help on this or anything.